Hello, this is Mr. Craig. All right. All right, so today we're talking about LeChatlier. And LeChatlier has a lot of things going on. However, it's really important to know about LeChatlier and what LeChatlier's principle is all about. So first and foremost, is the reaction at equilibrium?
Yes.
Yes, it has to be at equilibrium. If it's not at equilibrium, any of these things that we do to it, good luck. You're not going to be able to figure it out. And LeChatlier's principle deals with a stress that's imposed upon a system that's at equilibrium. So that stress could be a change in temperature, could be a change in concentration, a change in particles, a lot of different things. The first question here, it says, suppose the reaction that's given there has already reached equilibrium. Predict the effect that each of the following changes has on the equilibrium position. So whether it'll shift left, shift right, or not shift at all. So we're adding more of this reactant, UO2. Shift to the right? Okay, so what I'm hearing is that we are shifting to the right. When we add more of the UO2, Savannah, do you agree with that?
Periodic use.
Elizabeth? Shaking of the head. So, here's the thing. Remember that when we add more stuff, it shifts away from the addition and toward the removal. Grace has her hand up. Good question.
Why?
Okay. Riley is actually back in the back. Do you agree with this, Riley? With this, the class response to A. That if we add more UO2, that it will shift to the right.
Yeah.
Does everybody agree?
Yeah.
Sure.
Now I was going to say
That
wrong.
way, Mr. Craig.
Why does this not shift? What is the...
It's a solid. No.
That's the first thing I said. Did you hear me say that?
No.
No.
Oh, come on!
So, same thing that appears in the expression. Only things that appear in the expression will affect whether it'll shift or not shift. So, this will not shift at all because adding more solid. Now, the key here is when we talk about solids and liquids, that no matter how big or how small, the concentration doesn't change. Because you can think of it as how many particles we have per volume. So if the volume gets smaller, the particles per centimeter cubed stays the same. However, if we have gas particles, if we have our centimeter cubed, the number of particles will change, or the concentration. Sorry, I always have to start with that one to get everybody.
Anything about like your equations or any of that change if you add more? Your concentrations change?
Nothing will change if I add more solid to a system at equilibrium.
Because it's about the gas.
It's about the gases or aqueous, if we had aqueous, yep. So solids, if I just sprinkle more solids in there, then it won't change anything. However, will the system at equilibrium ever have no solid?
No.
Correct. You always have something, even whether it's a solid, liquid, or gas. It'll have some of that stuff. Because the system at equilibrium cannot be zero, or have zero of something. Because if I take the UO out, or if I take the uranium out, how's it going to make uranium fluoride gas?
Oh, you're right.
So we have to have some of that, even though it doesn't affect the shift. All right. B, the reaction is performed in a glass reaction vessel, and HF, which happens to be on the reactant side, attacks and reacts
With the glass?
with the glass. So where is glass showing up in this equation?
It's not.
Nowhere. So what is happening to the HF?
Gone.
It's being removed slowly
How do you know that?
because it's reacting with something that isn't in the equation. So by nature of the reaction, it's taking that away. So we are shifting toward the removal, in this case, to the left. Good.
Can you explain why?
Yeah, because if I take some of this out, does the K value change? Or the equilibrium constant? No. Okay. K remains the same unless what changes?
Temperature.
Temperature. Yeah, right.
Wait, okay, so sorry, but wait, so we know that HF is being removed because that's what's attacking and reacting with the
Yeah, and the key here is it's reacting with glass, and glass is not in this equation.
Wait, you're saying K doesn't change?
K will not change unless temperature changes. Now, what's going to happen is we're going to take some of that concentration out, and as a result, this is going to shift in that direction, causing the formation of more of this, which we don't really care because it's a solid, but it's going to drop these down and bring this back up, so the ratios will be the same. You don't have to know what those exact values are, which is nice,
Why
but
is K not changing?
because the temperature doesn't. So if the temperature changes, K will change. That's the easiest rule with LeChatlier.
Okay, but
Why
why
is
will
the
it
ratio
not
not
Why is the
change?
temperature changing?
It's not changing. I didn't say the temperature's changing, and
No, but
K is
like,
not changing.
If the temperature changes, like why does K change?
We'll talk about that here in a minute.
No, but why will K not change if you?
Okay, so what's going to happen is we remove some of this, so the concentration of the HF goes down temporarily. So as a result, as that goes down, we're going to reduce that amount as well. We're not going to have the same concentrations at the end, but they will adapt to get back to the ratios.
So you're saying like if you take out some HF, then the other two will go down too.
These will go down as well, and then we'll bring this back up. Won't go back to the original starting point, but the ratios will get there. Yeah, Grace?
Is the reason it's shifting left because if you have less HF, you can't make as many products? Is that why it's shifting to the left?
Yes, and also what happens to the ratio, let's say that we put our K up here. So K again is equal to the concentration of the products over the reactants. So when I take some of the HF away, this decreases. Therefore, to get K to be the same, I have to decrease this and bring this up a little bit to get that ratio back. What are the numbers? We don't care. Yeah, we don't care about that. All right. Water vapor is removed, so water is on the product side. So will we shift to the left, to the right, or not at all? To the right, because it's a gas, right? So as we take water away, we're going to have to shift it that way to get the reaction. Now, the UF is going to go up a little bit, but the water is down a little bit while that goes down. Again, we don't care about those actual ratios. We just know K won't change. What's the matter? What? Go ahead.
Just ask it because we.
Savannah, it's on the video. Come on.
You probably do it on
Yeah.
No, I was just asking, like, in terms of, like, the reactants, when do you know, like, what way it moves? Because Grace brought up, like, if it has less.
Okay. So anytime, if we take any of either the product or the reactant away, let's keep it respective. So let's say I take some products away. To get back to equilibrium, if I remove some of these, how do I get that back? These things will react and shift the reaction that way, so it'll form that. If I take things that are applicable, in this case, the HF, if I take that out, how do I get it back to equilibrium? I take these and shift it that way to form more reactants. Yeah, that's a beautiful thing about equilibrium. You're going forward and backward. Yeah, Eric.
So using the analogy in the first video where you have two different containers of a liquid and cups, is it just changing the glass, or the volume of the glass that you use to shift the liquid?
Possibly, yeah.
That's an analogy.
But we won't ever have to do that
Okay.
or think about it
I'm
that
just
way.
trying to, like, visually understand.
Yeah. Yeah, Maddie.
So when you say like shift left, you mean it'll form like more reactants? But that doesn't mean that no products are being formed, just more reactants.
So, good question. So what that means is when something shifts left, the rate in which the products form the reactant is greater than the rate in which the reactants form the products.
So there's more there's more reactants.
There's more reactants being formed than there are products being formed.
But there's still both are occurring at the same time.
Yes, so the rates are not equal. So eventually what's going to happen is we're going to get those arrows to be the same size, which means that we are now at equilibrium. That's a terrible arrow set, I apologize.
So that's why you use like.
That's why I use the two arrows, and they're the same.
That's why you use the big beaker and the small beaker, and then.
And then the volumes were the same, so that represented the rate at that point from that earlier video.
So, if you're shifting left, then basically the products
Are making reactants.
at a bigger volume or whatever.
No, don't worry about the volume of the beakers, worry about how much is being formed. And once we get to equilibrium, the rate in which these guys make that is equal to the rate in which that makes that. But if we have a shift left or a shift right, if it shifts right, the rate in which the products are being formed is a lot bigger than the rate in which the products are making reactants. That's really the concept that you need to know.
That's a shift.
That is a shift right, because the rate's much larger when the reactants form products. Yes, ma'am.
Okay, so it's like if there's more products, then you shift left. Is that like?
Ooh, what do you mean more products?
But like when Q, like going back to it, like.
If I take products away, I'm shifting right. If I add more products, I shift away. That's what I want you to know. Shift toward the removal, shift away from the addition, and we start at equilibrium. Yeah.
But usually that's like in
On
the
test
test
or the exam, are we gonna have to explain why we're shifting and the way we're shifting? Like,
Yeah, because we took something away to get it back. It's pretty much,
So you would just
Correct
say,
that next week.
yeah.
Just think about your resources.
Yes, Harrison, sorry.
Okay, so whenever something shifts to left or right, is that just like a temporary thing and it'll get back to equilibrium as soon as possible?
Excellent. That's exactly what it is. It's temporary to get back to equilibrium. Yes, Nisha.
What happens if you take away U of 2 in that equation?
If I take all that away, then we're going to shift that way, even though the reaction, we wouldn't ever talk about that.
Because you can't really make it.
Because you can't have zeros here.
and if you can't make us.
Yeah. So technically it's going to form, but you're not going to notice a change
But
in
really,
the
like, that
concentration.
shift left is just, you're not really being able to make any products.
Correct.
We didn't have any math with LeChatlier.
Nope. No math, all concepts. Yeah. So the quiz on Monday, you're going to be explaining or choosing the best option.
We have 30 minute video.
No.
Mr. Craig,
Wait, so it's no math?
in the video.
Oh, I didn't say that.
Oh, okay.
We were supposed to watch those.
Yeah, what?
Next.
All right, so looking at question number 2, it says predict the shift in equilibrium position that will occur for each of the following reactions when the volume is increased. So here's what So we've got a container at that volume going to a bigger volume. Okay? So let's throw this scenario out. Let's say that we have all of our gases in this little guy at 1 atmosphere. Okay? And then all of a sudden, the container gets larger. So will the pressure inside this container initially go from here to here? Will the pressure go up or go down? Initially it will go down, okay? Because if we look at the number of particles that we started with, it doesn't change until we do a shift. If the container changes, ideally we want the temperature to remain the same. There will be one situation or one scenario where the temperature will change, and we have it in our batch here. But let's find out. How many particles do we have on the reactant side for A?
4.
And 2. So we want to shift to the side that has more particles because we need to increase this pressure. So if we don't increase that pressure, if we don't increase the pressure, then we're not going to get back to the equilibrium constant of with those partial pressures. So in this scenario, the reaction will shift left to regain equilibrium. Okay?
Wait, hold on. Say that again.
Okay, so the container went from small to bigger, so it gave the particles more room to spread out. So initially the pressure went down. We need to get that pressure back to where it was. So what I need to do is increase the total number of particles available. So I'm going to shift to the side that would have or form more particles. So by adding more particles, then my pressure comes back to where it should be.
So that's saying that the rate in which products
Initially, yep,
change, or the products change to reactants will
be greater. That's what the shift is. So whenever we talk about shift left, shift right, we're talking about the initially, that rate after the change is greater for that direction. Yes, Maddie?
What's the definition of pressure?
How many times a particle strikes the side? How often?
So like the more particles, the higher pressure.
Yes. Yeah, Nisha.
Why do you need to have more particles?
Because there were X number of particles in here, and if I bring those same particles over here, think about how often it'll collide with the sides of the container. As the gases,
Pressure have to be the same.
that's why we want to increase the number of particles to get the pressure back up.
Like, why does the pressure have
More-
to be the same?
Because that's equilibrium, that's LeChatlier. So whenever we do a K sub P, it's all about the partial pressures of that gas, whatever we have there.
So you're adding more reactants so that the pressure will go up
Yes,
and K will stay the same.
yes. So the ratios will change. Mathematically, we won't ever worry about that. Yeah, Julie?
So basically, it wants to make more reactants because those take up more space, and now it has a bigger container and it wants it to be filled up just like this one.
Yes, and also when the temperature is at whatever the temperature is, if I increase the temperature, what happens to the rate of the gas particles? They speed up. So if the temperature remains the same, we have to have more particles if we're going to get back to whatever pressure we had here.
Wait, okay, wait, going back to what Julia said about, something about want more reactants to fill it up more or something. Can you
I like that.
Yeah, can you explain, I'm confused.
Okay, so we're dealing with pressures. So if we had originally 4 particles in the container, and then we expanded the volume without changing the number of particles, what happens to the overall pressure inside? It goes way down, yeah. So we need to increase the number of particles, and if it goes from 4 to 2, we're going to increase the total number. Now you're probably locked in on 4 and 2. That's not the case.
So you can increase the number of particles by increasing the rate of the reaction?
Initially, that's what shift means. So we're increasing the rate initially to get this number to influence our partial pressures.
Wait, when you say increasing initially, what's?
Just shift left. That's all I want. Yes, Grace.
You can't change, you're trying to increase the number of particles, why can't you increase the number of particles of it?
Yeah, like why can't you
Okay, so
do product?
if, now listen, guys. If I shift this way, I'm going from 4 to 2. I'm actually reducing the number of particles,
So you lower pressure.
which is thus lowering the pressure even more. So whenever we shift in that direction, we're looking at the end result.
So you're going from 2 to 4. That's
Yeah,
what
so
we're
that's why if we want to increase the partial pressures, we have to get more of those available. Okay. And keep in mind, KC and KP aren't the same.
Wait, so will that work for every single one? Like, that
We're going to go through the scenarios, yeah. We're only on the first one. All right. Let's look at B. How many particles on the left? How many on the right?
2.
So which way will it shift under those conditions?
Right.
To the right.
Now we're on.
How many particles?
2.
How many?
2.
Will we shift?
No.
There will be no shift.
Change the temperature to.
The temperature will change. Now,
Pressure increases.
so we have PV equals nRT, and remember, R is a constant, so pressure and volume change. Now, we're not going to do any math on that, but these are changing, therefore the temperature will change. It'll go up or down. We don't know if it's inter or exo. That's coming up here.
Whoa. Go back up.
What's that?
Why did PV equals nRT just come?
Because the temperature will change if I have the same number of particles. Let's pretend that we only have 4 particles in there. The temperature has to change if the pressure and the volume change,
So if you increase that, did that.
It's gonna increase.
based on PV equals nRT.
Yeah.
So we have to change the pressure, but we can't change the pressure because there's an automation.
Yeah, based on the math, it'll
Just,
change.
where does that energy come from?
Don't worry about where it comes from.
Well,
It's somewhere. It's in the universe.
okay. So it's just going back to like the thermodynamics thing where there's energy everywhere.
It's everywhere. That's the beauty of energy.
We'll call that Jesus energy.
Whoa, whoa, whoa. Keep that up. All right, so looking at D, we go from 1 to
Say for C.
no change.
You just say no change.
No change, no shift. Therefore, and if I asked, will K change? You would say yes. How? We don't know. We would need more information. Yes.
So for the quiz on Monday,
Quiz is on Monday.
what like
All right, looking at D, which way will the reaction shift?
Right.
Right.
To the right, to form more particles. What about E?
Right.
Right.
Wait, is there solid?
There's a solid.
Oh, dang. What that means?
So how many particles on the left? How many on the right? Will this shift? Yes, to the right. Number of moles of SO3, which happens to be what? A reactant or product? A reactant, very good. It's right there. Alright, so in each of the following cases, oxygen is added. So will we shift left, shift right, stay the same?
Shift left.
Okay, so we're going to shift to the left. And let's answer the question. So SO3 will, say it again, Grace? Increase. Okay.
What's gonna increase?
Number of
Number of
Oh,
moles,
like if
number of
it's
particles,
molarity.
number of particles.
Particles.
All right, the pressure is increased by decreasing the container. So which way will we shift?
Left again.
Because we have 2 particles here, 3 here, so we shift that way. So what will happen to SO3? It'll increase again. Good.
This is hard.
No, letter C. We add more argon.
Oh, that's
no.
another gas.
On which
gas.
wait,
It's an
but
inert
it's
gas.
an endothermic.
No, I'm looking at C.
It's inert.
It's a
It
random
doesn't do
gas.
anything.
That doesn't react.
So there's no shift if you add argon?
It's an inert
But it's adding pressure.
No, that's inert, Mr. Gray.
It's a nerve
No, it's
gas.
Riley? Hang on, Riley.
It's a what?
It's
It's not in the reaction.
it's a noble gas. It's anything that's not included. So it's unreacted. It's just a participant.
Oh, it's a nerve gas.
Because it's not in here.
Oh, okay.
So if I put nitrogen in there, it wouldn't do anything.
What about if you put krypton?
Ooh.
Kryptonite.
I'm surprised you know what that is.
But
I can't believe kryptonite is a real thing. Isn't that crazy?
Wow.
Is it?
All right. Letter D. Finally, we're to the temperature aspect. Okay.
No, wait, did we put no change?
We put no change for C. Because adding an inert gas affects the pressure on both sides, and it's not in the equation. So, all right. D, the temperature is decreased. But before we do that, we have to look at this equation, and there's some information given. So it says that we are adding energy, or are we removing energy
That's,
by having the reaction occur?
isn't it product?
Hang on here. So a reaction is either endo or exothermic. There is no, it's not like an inanimate object that absorbs energy and it's like, oh, that's endothermic. Or it loses energy and that's exothermic. It's like you are an exothermic process. That's it, you're exothermic. When you stop doing exothermic reactions, you're dead. Done, okay? So this is a what, endo or exothermic reaction? Endo. Therefore we treat endothermic as what, a reactant or a product?
Reacting.
So we can put it over here, so it's a reactant.
Temperature's decreased.
And the same axiom that we used about if we add something, what do?
Shift away.
Shift away. If we remove, we shift toward. Okay, so temperatures decrease. Are we adding energy or removing energy? Which way are we shifting? Toward the removal, which is energy is on the reactant side. Therefore, SO3 is decrease. Increasing. Yes, sorry.
Wait, well,
Sorry.
Mental typo.
Wait.
So if the temperature is going down, that means I'm putting heat into it. Or I'm sorry, in this case, I'm removing it. I'm putting it in an ice bath. So the ice absorbing the energy. It's taking the energy away. Now, you're confuddled because it says it's endothermic.
no, I don't understand what happened.
Okay, so if a reaction says that it's endothermic, the energy is treated as a reactant. If it says it's exothermic, we're going to treat it as a product. So we don't get to flip and say, okay, this time it's endothermic, tomorrow it's going to be exothermic. Your whole life will be an exothermic reaction.
Your whole life.
Feels warm. Yes, that's good.
Yes.
Yes, Brian?
Okay, but why does that mean that SO3 goes down?
Okay, so if I take heat away, I'm taking energy away. I'm essentially taking a reactant away. Therefore, I'm going to shift in the direction that will be added to it. So we treat energy like a reactant or a product. Yes, ma'am.
So why does that mean that?
Because if we shift that way, SO3 increases. Now, let me ask you this. Will K change?
Yes.
Yes.
Because
Because it
temperature.
involves temperature.
Yes, Riley.
Okay, so say that, if the product reactions were switched or whatever.
Okay.
Two SO2 and oxygen were on the left.
Okay.
That means that SO2 and O2 would both increase.
Yes, if, we'll pretend it's endothermic and those are flipped. Yes.
So they both.
Yes.
Well,
Yes, Brian.
So delta H in equilibrium is a net value, right?
Yes.
Because if you're going here from, to make SO2, SO3 be XO3, what more energy is absorbed than right?
I'm not sure what you're asking me there.
So like making SO2, O2 is an endothermic reaction.
It requires
It
energy
requires energy.
for the reaction to proceed.
Making SO3 is exothermic, but the net is positive.
If we flip the equation, it would be XO. Yes.
That's what I'm saying.
All right, we good? We're going to get some more temperature. Oh, yes, Maddie B.
Why does K change?
Because the temperature changed, so your concentrations will be different. Gaseous sulfur dioxide is removed, so we're taking some product away.
It's gonna shift to the left.
Shift to the right.
To the right, therefore SO3 will
Go down.
go down. Good, awesome. Whew. Now we get to the part that everybody's been wanting to know information about.
It's gonna get more confusing.
Oh, are we
What is the
about
whole process?
Okay,
It's just gonna make
don't
it
get
more
distracted by the names. Focus on the question.
No, not for the course, I'm just
Dude, we had to
curious.
study the Haber process.
We don't have time for that. Because Kate, Mr. Craig, am I gonna get more confused by this?
Okay, hopefully.
Directly using iron.
All right, ammonia is produced by the Haber process in which nitrogen and hydrogen gas are reacted directly using an iron mesh impregnated with oxides. Very
Why
good.
would you use
Cross
pregnant?
out that one.
Because that's what it did.
Consider it intertwined.
Mr. Craig, that is not full of
The equilibrium constants.
This video is being demonetized.
The equilibrium constants are in this column right here. Okay?
No
And the
way.
temperatures
Don't
are
spoil it,
in this column right here.
Cooper just spoiled it, Mr. Craig.
K sub
I don't know, I might be
K
wrong.
sub
All right. So, don't worry about the K. Sub P or sub C. We don't care. So, to answer this question, is it exo or endothermic? The first thing you want to do when given information like this is determine the shift. Determine the shift. So looking at the top temperature to the bottom temperature, has K increased or decreased?
Decreased.
Okay, so let's put this up here. I would agree with you on that. So if K decreased, then that means what to the products?
Products are going down.
Going down, and the reactants are going up. So which direction is the shift?
Left.
To the left. That's the hardest part right there, determining the shift.
That's easy, bro.
Okay.
I'm just kidding. It's probably gonna be hard.
All right, so now the next thing is, as I go from the top temperature to the bottom temperature, the temperature has increased as a result of what being added? Energy. So, am I going to put energy over here or over here?
Over here.
Over there.
Wait,
Right where your finger is.
Right where
Okay.
Right where your finger
So as I go from the top temperature to the bottom temperature, did the temperature increased? As a result, was energy added or removed?
Energy goes, why?
Riley, say it again.
Energy goes on the right.
I don't want that. I want to know, was energy added or removed? Because that's the key. So we're adding energy. So if we're adding energy, do we put it over here where the arrow is shifting toward me? Or do I put it over here where the arrow is shifting away from me?
Duh, Mr. Craig. This is
Well, what's duh? I don't know what does. Is it reactant or
It's
product?
going away. Exothermic.
So energy is shifting, the arrow is shifting away because we're adding more energy. So the same thing, whether you add concentrations, you add pressures, you shift away from the addition, you shift toward the removal. Therefore, is this endo or exo?
So it's X.
Okay. Let's do some more.
Oh no,
Oh yeah.
there are no more.
Oh, there are.
No.
If you pull us on.
Hang on, let's go to the fun part. Here we go. Number 5 on day 67. More practice. Number 5 right now. Okay. All right. So we're looking at a system that's at equilibrium when the following conditions are changed. Determine if the reaction is endo or exo. And we're going to go through whether it's endo or exo, whether we're adding or removing energy, or if the temperature is going up or down. Pretty cool. So, let's take a look at this first one.
What system?
Yeah, don't worry about it. A system at equilibrium. So, worry about the shift first. So, K, it says K is decreasing. Riley, what is happening to the concentration of the products?
Products are going down and reactants are going up.
So whatever K is doing, that's what the products are doing. That's the easiest way to remember it. Okay? Whatever K is doing, that's what the products are doing. Therefore, if the products are decreased and the reactants are increased, which way are we shifting?
The left.
Riley?
That's not narrow.
Why?
Because, wait, say the question.
Okay. So if the products are decreasing and the reactants are increasing, will I put the arrowhead over here or on the left?
By a bigger number, so it's
Products are being decreased. Just say we're using products to make reactants. Okay, so we have the shift. Temperature decreases. So are we adding or removing energy?
Removing.
Riley?
Oh.
Removing? So is the arrow currently shifting away from me? Yes?
yeah.
And is it currently shifting toward me or pointing toward me? So where do we want to put the heat?
On the right. What? Oh.
Shift toward the... There's two things. Shift toward what? Shift away from what? It'll go for everything. That's the nice thing. That's why I keep saying it over and over again.
Wait, no, now I'm confused. I thought the E went on the opposite side of the arrow, so
Oh, no. We don't think about opposite sides. We put it on one side or the other based on how this is shifting. And that the temperature is, are we adding or removing temperature at this point?
we're removing it.
Therefore, this side,
On the left side.
does everybody agree with that?
Yes.
So is that endo or exo?
Endo.
Endo. There we go. All right, looking at B. The temperature increases and K increases. So which direction is the shift? Toward the product side? And so we're shifting away in this case? Riley? So we're increasing. So that means we're adding or removing?
We're adding.
We're adding?
So it's going to be on the left.
On the left again?
Yeah.
Good. So it's endothermic. And if you could remember, shift away from the addition, shift toward the removal. Don't worry about which way the arrow's pointing. Just keep that statement in your head. Okay? Let's look at, here we go. C, K changes from 12 to 3.5. So did it go up or down?
Down.
Went down. Okay. Therefore, the products did what, Riley? Went down. So which way is the shift? Which way is the arrow pointing? Left or right? To the left? Does everybody agree with that? Okay. And then, so, wait a minute, we're over here. Heat is added. Where's heat going? Shift away from the what? shift away from the
Addition.
addition, put it on the tail end. Don't try to think about endo-exo. Answer that question after you've done all the work. Okay? All right. Let's take a look at the next section.
Oh, we just,
We skip D.
Let's look at E real quick. We'll skip D for a second. Okay? What's the matter, Raya?
No, it's really, okay. When it says 12 to 3.5, is
Uh-huh.
that saying that 12 is on the website?
12 is a higher value. 3.5 is a lower value. So the value for K, the equilibrium constant, decreased. It got lower. That's all it means. Don't worry about high or left or right. Just means that it decreased. Yes, ma'am.
Was that an exothermic reaction?
It was, so heat was added. Yes, it was. All right, let's look at D. So K, does it get bigger or smaller?
Bigger.
So shifting left or right?
Right.
Right.
Shifting to the right. Are we adding or removing energy?
Moving.
Removing. So where do we put the energy?
On the right.
On the right. So it's endo or exo?
Exo.
Excellent. 6 is changing it up. Now it wants to know, is the temperature increasing or decreasing? In other words, are you adding heat or removing heat?
Did we say exo?
What was for E?
I don't remember. All right, so same thing. It's exothermic, so is heat on the left side or the right side?
Right.
Right.
Okay, it's on the product side. Okay? And it says that K is decreasing. So which direction is the shift?
Left.
Left.
Whoa.
Left.
Riley, you good? Do you agree with that? That we're shifting that way? As a result, is the temperature going up or down? Are we
Down.
What? Toward, away from the addition.
Here's our scenario.
Sorry.
K decreases and it's exothermic.
It's up,
Up.
because it's going away from the addition.
What?
K, the value for K decreases as a result of either adding or removing energy. What are we doing physically here with this representation? Are we shifting away or toward the energy?
Away.
When you shift away, what are you doing? Adding. Therefore, the temperature is increasing. Talk through that. Don't try to think through that. Yes. Let's do, wow, that was jinky.
you guys sound like Greg, don't you?
Let's look at B. Okay?
No change.
Endothermic and K does not change. So
No change.
the temperature doesn't change?
Nope.
Because when the temperature changes, what
K
changes?
changes.
Very
Every
good.
time.
Looking at C,
Yes.
K changes from 3.5 to 12. Is K going up or down?
Oh.
So is it shifting left or right?
Right.
Because we're making more products. And it says that the heat of formation is negative 400. So is that endo or exo?
Exo.
So it goes over here. Are we adding or removing energy?
Removing.
There we go.
Dab on that.
Okay. Now we got another scenario.
More. Jeez. You are full of surprises. You're full of surprises.
The system is at equilibrium when the following conditions are changed. Determine if the K, the equilibrium constant, is increasing or decreasing. Okay? So it's exothermic, so that means heat is on
The right.
the right. Oh, shoot, sorry. So heat is over here on the right. And it says that we're adding heat, so which way are we shifting? To the left or to the right?
Left.
So we're shifting away.
So K is going down.
So K is
Decreasing. Decreasing.
decreasing.
Got him.
Wait, how'd you just figure out K was decreasing?
So it's exothermic. You're adding something, so we shift away from the addition.
Yeah, but how does that mean?
Well, here's your shift right here.
Right, P and R.
What is happening to the product that, sorry.
Oh, I see.
So the products are decreasing while the reactants are increasing. There you go. All right, endothermic, left or right?
Left.
Left. Heat is removed.
I think.
So is the temperature being going up or down?
You mean K?
K, sorry.
K is going down.
K is going down. Good.
I whispered that
Last
to you.
one, K is going.
Sorry.
Sorry.
And boy.
K is going.
So the temperature is increasing, but let's start on the endo or exo. Are we in right or left side?
Left.
Wait, how do we know that?
That's a good question. So it's endothermic. So is heat is over here, and it's increasing. So we shift away. Therefore, K is increasing.
Duh.
Wait, what's so crazy?
What is so crazy?
What's that?
Because you're increasing the other.
Because you're
Because you are increasing the temperature.
increasing temperature and it goes away from the expression. Are we gonna know how to find K sub EQ?
Yes.
By
That's
the.
just K. So that's what we did on Monday and Tuesday.
Okay, well, I was like doing a thing where I like go through all the old exams, like first questions.
Don't worry about it, it's Craig style.
I know, but for the test.
You would, so what I'm doing is equilibrium, the way that College Board has it set up, is they want you to do equilibrium with this and KSD. So in other words, solubility product. I'm saving solubility product for right before the AP exam. So if you can do the calculating K based on the concentrations and pressures, you're golden.
Can I talk to future Mr. Craig?
So if I can tell
Future
that,
Mr. Craig, I know I'm your
like, okay, we knew
favorite.
that K was decreasing on this, then how can I figure out what